Hey guys, Dr. Cadell here, and this is the Density and Graphs Lab. The idea in this experiment is measuring density, and in the third part C of this, we're going to use the density that you measure of a salt solution to figure out its mass percent sodium chloride, its composition. So let's start with the density. The formula for density is D, which stands for density, is equal to mass, we write M for that, divided by the volume, V. Which means if we want to find the density of some object, we need to know two values, the mass and the volume. And that's what we're doing in this experiment for the most part. In the first part of this experiment, we're going to figure out the density of a metal cylinder. And a metal cylinder, because it is a geometric object, a shape that we can calculate its volume of by taking a couple of measurements, it's pretty easy to get the density. So for the cylinder, we get the mass by measuring its mass on a balance, which is pretty easy. To get the volume, we're going to calculate it. Now to calculate it, if we look over here, we're going to use that formula right on top. And I give this to you in the lab report, so don't worry about this right now. But the volume of a cylinder is equal to pi times r squared h. R stands for the radius of the cylinder, and h is the height or the length. And I'll show you what those mean in just a minute. So that means that in order to calculate the density of this metal cylinder, we have the mass because we weighed it. We're going to need to get the radius and the height. So if we look at this picture right here, okay, this will be the side of the cylinder. All we do is we measure from here to here, and that's h, or the length, if you will. We're going to measure that distance as well as the other one in centimeters. And just remember, it's going to be 2 places past the decimal. So what this represents here is the end of the metal cylinder, the round portion. And we can't measure the radius directly because the radius is halfway through and we'd have to estimate where that is, and we can't really do that very well. So what we do is we measure the diameter. Now the diameter is just the largest distance that we can find from one side to the other. We're going to use a ruler, we're going to measure it in centimeters, and it'll be 2 places past the decimal. Once we get the diameter, all we have to do is, and we'll do this in the lab report, is divide that by 2, and that gives us the radius, which is what we need for our equation to calculate the volume of that cylinder. That's the first part, the metal cylinder. We go to the second part of the experiment, where we're going to determine the density of some unknown metal shot. The thing is that with metal shot, there's no uniform shape. We can't calculate its volume, we can't just use a formula. So we're going to use water displacement to determine the volume of that metal shot. The mass is easy. We do it the same way as we did with the metal cylinder. Just weigh it, no problem. To get the volume though, what we do is we're going to take a graduated cylinder, fill it about halfway with water, read its initial volume, take the metal shot and pour it into the water. The volume's going to rise because there's more stuff in there. We're going to read the new volume, and the difference between those two volumes is the volume of the metal shot. And that's the second thing that we need for the density calculation of the metal shot. Now it ends up, you're going to do this in the lab report, that knowing the density of the metal shot, you're able to determine what metal it is. Because what I do is I give you a list of the possibilities and I show you what the density of each of those is. The density of each metal is pretty much unique to that metal. So all you do is you find the density that's closest to the density you calculate, and that tells you what metal it is. And that's the second part, the metal shot portion. In the third portion of this experiment, we're going to determine not only the density, but you're going to use that density to find the mass percent of sodium chloride in an unknown solution. So if we come on over here, guys, and now we're talking about the third part of the experiment, the unknown salt solution. The idea is we're going to measure the density of that salt solution. Well, we're going to calculate it by taking some measurements. Again, we need the mass and the volume. Mass is easy, we're going to weigh it out. Volume's easy for this part too, because what we're going to do is we're going to use a volumetric pipette, which I'll show you how to use when we get over there to the experiment, to measure out 10.00 milliliters of the unknown salt solution. And that's important. So for the volumetric pipette, it's 4 significant figures, 10.00 milliliters. So that's what we measure out. And every time, we're going to do it 3 times, and every time the volume's going to be 10.00 milliliters. So now, bottom part's easy, and we just weigh the mass on the balance of that 10.00 milliliters. Now we have the top part. Now once we get that, we're going to do a little bit more with this part. You're going to measure the density, well, the mass and the volume of your unknown salt solution 3 times, take the average. Now we're going to use that average density to figure out how much sodium chloride is in that unknown solution. And the way we're going to do that is we're going to use a graph. If we look at this, it ends up that there's a linear relationship between the density of a salt solution and the mass percent of sodium chloride that's in that salt solution. That means if we make a graph of density versus mass percent, we should get a straight line. Now what I've done for you in the lab report is I've basically done that graph and I got the equation of that straight line. This is what you guys need to use for that. And I take you through that in the lab report too. So in this equation right here, this is the equation of the straight line for density versus mass percent sodium chloride in a salt solution. Here, Y is the density, in grams per milliliter. X, this is an X right here, that's the mass percent. So what we do is we take this equation, which I've already got for you, and you're going to take your density and replace Y with the number you got for your density. Solve this equation for X. And I walk you through this in the lab report, do the algebra and all that. Solve it for X and get X. Okay, you're going to calculate X. That will be how much sodium chloride is in your unknown salt solution. All right, so guys, I'd just like to remind you how to read the ruler for the metal cylinder and the graduated cylinder for the metal shot. When you look at the ruler, first we're going to use the metric side. The metric side, it probably says something like mm and cm. What that means is the smallest marks are each a millimeter. The larger marks are each a centimeter. We read it in centimeters, and what that means is the smallest marks are 1/10 of a centimeter each. And because the closest marks are 1/10 of a centimeter apart, that means we record any measurement we take with this tool to 2 places past the decimal. So for example, if we were measuring this blue line right here with this ruler, we'd put the left hand on the 0. By the way, note that the 0 is not the end of the ruler, it's a little bit in. So we line this up with the 0, and then we come over here and we say, all right, it's between 1 and 2, so it's 1 point something, and we go 1, 2, 3. It's not quite 1 to 1.4, so it's 1.3 something. So now we estimate about how far over past the 0.3 it is, and I said that's about 1.31 centimeters. If you said 1.32 or 1.33, I wouldn't argue with you. That part's estimated, we understand that. Now for the graduated cylinder, for the metal shot, in part B. Remember, we read the bottom of the meniscus. In our graduated cylinders, the closest marks are 1 milliliter apart. They're in the ones place. And so what that means is we record any measurement we make with that graduated cylinder 1 more place to the right, to the 10th place, 1/10 of a millimeter. And it's understood that that 1/10 is estimated. So if I were reading this, I would say, all right, the bottom of this meniscus is between 20 and 25. So it's come down here, 21, 22. So it's past 22, but not quite to 23. So now we estimate to the 10th place how far it is between the 22 and the 23. So I'd say it's about 22.2 milliliters. But again, if you said 22.3 or 22.4, I couldn't argue with you. And that's all there is to that. So why don't we come over here and get started. All right, guys, so we're going to start with the first part, the metal cylinder. Really easy. All we do is measure the height or the length and the diameter. To measure the height, we just place one end against the 0 on the ruler, read the other end, 2 places past the decimal in centimeters. Now to measure the diameter, we're going to take it, and what I do is I line up the 0 on one side and I move it up and down until I find the largest distance. And that will be the diameter. Once more, in centimeters, 2 places past the decimal. Now, you're all going to have your own measurements for that. And then the other thing we need for this, by the way, the length is going to be your A2, that's in centimeters. The diameter will be your A3 in centimeters. And finally, the mass, this is A4. So we put it on the balance. We can just put it directly on the balance. So we make sure the balance reads 0 first by tearing it. Place this on the balance. Record that number 3 places past the decimal, a little g for grams, that's your A4. And that's all there is to the first part, part A. Now for part B, the metal shot, we're going to measure the mass. Now with these, if you're getting this data at home, you will not have an unknown number. But if you're actually doing it in the lab, there will be an unknown number. So if you do, take it off and tape it in your data table. To get the mass of the metal shot, you take an empty beaker, place it on the balance, and tear it out, because we don't care how much that beaker weighs. There we go. So now it says 0 with the empty beaker on there. We take the beaker out because we never pour anything directly onto the balance. And when you're pouring this metal shot into the beaker, you've got to be careful. Some of this metal shot is pretty dense. If you just dump it in, it'll break that beaker. Place it back on the balance. Get that mass. That's your B2, mass of metal shot trial 1. 3 places past the decimal, little g for grams. Now you're going to do this part of the experiment 3 times. So, you go through, you do the, everything here, then you repeat, and that's when you take the mass the second time, that'll be your B5, and then the third time will be your B8. Once we have the metal shot weighed, it's in the beaker. You're going to take a graduated cylinder and put some tap water in it, just about halfway, and you're going to read the volume, the initial volume of that water. Each trial. The initial volume for the first trial will be your B3. Remember, this is 1 place past the decimal, and it's in milliliters. Read that and record it. Once you get that, take the metal shot and once more carefully pour this into the graduated cylinder. Careful not to splash any water out and not to break the graduated cylinder, because some of this metal, if you pour it too fast, it definitely will break that graduated cylinder. And you got water everywhere, and you need a new graduated cylinder. Now what happens is sometimes bubbles of air get trapped in here, so what you do is gently tap it on the counter, make sure everything's settled in, no water bubbles in there. Now the level is higher because the metal shot's in there, so we read our new volume, 1 past the decimal, milliliters. That'll be the final volume, that's B4. And then we do this for the second and the third trial, and that's all there is for the second part, metal shot. And the third part, the unknown salt solution. Once more, unknowns come with an unknown number. So if you're actually doing this in the lab, take the unknown number off, place it in your data table. And if you're just getting the data at home, you will not have an unknown number. So we need to know the mass of 10 milliliters of this solution. So what we do is take an empty beaker, place it on the balance, tear the balance. Now it says 0 with the empty beaker on there, and we're going to use a volumetric pipette to transfer 10.00 milliliters of unknown solution into the beaker. Never transfer anything directly onto the balance, so we take the beaker out. Make sure we don't touch anything there so we don't lose our tare. So with a pipette, remember there's a mark up here on the neck somewhere. We want the bottom of the meniscus just touching that. So we're going to pull the solution up above there somewhere and then adjust it down. Pipette bulb, pipette. So again, remember with this, you want to make sure that the pipette is dry, the top of it, your forefinger is dry, and the pipette bulb is dry. Because if any of those are wet, this part's pretty much impossible. And again, remember there is a mark up here. It's going to be somewhere, they're all different, on this top part of the pipette. You want to bring the solution up above it and then let it go down until the bottom of the meniscus just touches the top of that line. So squeeze the pipette bulb, leave it squeezed, put it on there. Don't have to jam it on, just let it seal. Pull up the solution above that line. My line is right there, so I'm going to pull it up here somewhere. Take it off, put my finger on here. Now, I want to get the bottom of that meniscus just touching the top of this line. So what I'm doing is I'm releasing a little bit of pressure with my finger and then twisting the pipette. And I can control it pretty well that way, as long as it's all dry. If it's wet, you get a seal there, and it's just really frustrating. There. Transfer it over. Remember, we want to let gravity pull that solution out. We don't want to push it out with a pipette bulb. All right, once it's finished draining, we touch the tip to the side of the beaker, place it back in the balance, record that mass to 3 places past the decimal, little g for grams. Now we're going to repeat this part 2 more times for a total of 3 times. When you finish with this, after you get this measurement, you can dump this solution down the drain, clean it out, dry it out, and then do the same thing 2 more times. And that's all there is to it.